Hello once again, class, and welcome to another mock lecture. What I've prepared for us is a few videos on prerequisite information when you're entering a college algebra or a pre-calculus class. And these ones are geared towards a specific class, Math 111Z. So all of these videos that are called this 111Z prereq are going to be things that you're kind of assumed to know going into the class. So take these as a bit of a refresher course for you. I'm not going to go in super detail on a lot of stuff, but I'll hit the basics, and hopefully as you watch this, you're kind of starting to remember some of the stuff that you learned before. Anyway, that was a long-winded explanation for what these videos are. We're going to start off with functions. Now, before we talk about functions, we have to talk about kind of what functions are made up of, which is a relation. What I have on the screen here is a tabular representation of a relation. There's a whole bunch of different ways that you could represent a relation. Tables is one of them, where you have your x values, your inputs on the left-hand side, and your y values, your outputs on the right-hand side. But what's a relation? A relation is just a set of ordered pairs, right? And so I'm choosing to represent it as a table of values here. But, this has the ordered pair 0, 4, and the ordered pair 1, 6, and the ordered pair 2, 7. If you don't remember what an ordered pair is, it's just a location on the Cartesian coordinate system. So if I wanted to plot 2, 7 on here, it's just right here. Over 2, up 7, right? X and then Y is how we would do that. Right, here's some other points on the relation. Put 1, 6 on there, 0, 4 is on there, 1, 3, so on and so forth. So here's another representation. This is a graphical representation of this specific relation. But at its core, a relation is a set. So the set is notated with these kind of curly brackets, which is to say, hey, this is a container that has stuff in it, and the stuff that a relation set has in it is just a bunch of ordered pairs, a bunch of locations on the Cartesian coordinate system. Now, anytime that we're talking about a relation, you kind of have to also talk about two other sets that exist within the relation. One of them is called the domain, which is the set of all the x values that are in that specific relation. And here we can actually just see them. They're the discrete values 0, 1, 2, 3, 4. Notice that while 1 does show up twice, it's only showing up one time in the domain. Once it's in there, it's in there. We don't have to put any repeated values. The other set is called a range, which is the set of y values. So here the y values are 3, 4, 6, 7, 11, and 24. You'll notice that I put mine in order. You don't have to do that. Sets that contain the numbers 1, 3, and 6 is exactly the same as the sets that contain the numbers 6, 3, and 1. Right? The order of them doesn't matter inside of the set. Okay, so we know what a relation is, right? It's a set of ordered pairs. But if someone were to walk up to you on the street and say, hey, what's a relation do? Well, that's a different question, right? There's kind of two sides to the learning coin, if you will, when it comes to mathematical entities like this. One of them is a stipulated definition, set of ordered pairs. That's what a relation is. But the concept image can help us answer the question, what does a relation do? So how do I think about relations? How do they actually work? Well, for me, I think about it in terms of cities. So I'm going to actually, I've got two kind of blobs, if you will, on the screen here. One of them is called domain, one of them is called range. And I think about the domain and range as cities where the specific domain values of your relation and range values of your relation live. And let's say that there are numbers that are in the domain that would like to move to the range. So let's say 0. Right, in domain land wants to move to range town. So like it's akin to getting on a plane and moving their life to range town. Well, the plane, right, the transportation machine, could be a train, maybe it's a car, maybe you're just walking. Maybe domain land and range town are like a mile away. I don't know why that's important. The point is, if 0 wants to move, the transportation machine that it needs to take is whatever the relation is, which is some kind of mapping from the domain to the range. But when 0 gets on the relation, when it gets on the transportation machine, it undergoes a transformation and it winds up in range town as the number 4. Same thing happens to all the other numbers. 2 becomes 7 when it takes the relation transportation machine. 3 becomes 11. 4 becomes 24. 1's a little weird because it becomes 3 or 6. Right? Maybe it flips a coin and decides it becomes 3 or 6. I don't know. But that's how I think about it. This is called a mapping diagram. But I think about it as Things in the domain want to move to the range, so they get on the relation and become some other number in the range. They're being mapped to another number in the range. But what does this mean for functions? Well, a function is a relation. So everything that we just said is true for functions. It's a set of ordered pairs. It has a domain and a range. It can be thought of as a mapping diagram, right? Numbers from the domain want to move to the range. They take a function instead of it's just a relation, which is like a super relation. But what is it that makes a function different than a relation? It's really just one thing. The one thing is that every single number that moves from the domain to the range can only be mapped to a single number. Said more mathematically, I wrote each element in the domain corresponds to exactly one element in the range. But thinking about the concept of numbers moving from the domain to the range, when they move, they are only mapped to a single number. So if we look at our example, let's examine this. Let's ask ourselves, is this relation that we talked about at the very beginning a function? And the answer is no, right? While it's true that 0, 2, 3, and 4 all get mapped to just a single number in the range, 1 does not. 1 either becomes 6 or 3. There's 2 arrows emanating away from domain land. So because of that, this relation is actually not a function. 1 becomes 3 or 6. 1 gets mapped to 3 or 6. That compromises the definition of a function. To determine what a function is, you just have to keep the one rule in mind. Every element in the domain gets mapped to a single number in the range. So let's look at some of these different representations of relations and determine, are they functions or not? Or are they just a relation? Well, let's look at A. For the x column, I do not see any repeated values. It is true that they all go to the number 2, but if we were going to draw a mapping diagram of this, and I'm just going to put like little dots for the different things in the domain, because they're all different, and then there's only a 2 here. Well, they would all go to 2, right? But that's fine. Every single element only has one arrow emanating away from it, so every number is only mapped to one number. Turns out every number is mapped to 2, but that's fine. So A is a function. Put a little check mark there. B also looks like a function, right? Every single shape, triangle, circle, square, and cross, only one arrow or one line is connecting it to something in the range. So B, also a function. C is something that's of the form y is equal to mx plus b, which means that when you graph it, it looks like a straight line like this. And if you pick any x value along the x-axis, it's only going to be mapped to one y value, right? No matter where you put it. Right? It passes what we call the vertical line test, which says that if every vertical line that you can draw intersects the graph no more than one time, then your relation is a function. Okay, E, I can see right away is not a function. 1 goes to 7, 1 goes to 10, so E is not a function. I don't know why I skipped D, but we can do D right now. D is also not a function. It does not pass the vertical line test. Here's one x value that ends up having 1, 2, 3 different outputs, right? So that is certainly not a function. Now, once you know that something is a function, we can use what's called function notation. Function notation, and again, you have to know something's a function first. And I don't know exactly off the top of my head what x squared minus x minus 2 looks like, but I do know that it's a parabola that opens up. And if I pass vertical lines through this thing, we're going to find that it only is ever intersecting one time. Okay, so this thing is a function. Well, when you know something's a function, you can change the notation away from y is equal to some stuff in terms of x to f of x. What we've done here, and again, this is just notation. I think a lot of students see this and they're like, what's f times x? But that's not what's going on here. F of x is just the notation for this thing being a function. The thing in front of the parentheses x is the name of the function, and then the thing that's in parentheses is the variable that the function is in terms of. So sometimes you might see something like, h of t, which is the function's name is h, maybe it's modeling height, and t represents time. So it really depends kind of on the situation that you're in, but f of x is the most generic way to label a function. And again, the way that you read this, right, the way that this thing is actually read is f of x. Now this has two useful purposes. Function notation, that is. The first is that you can really easily see input-output pairs, like when you're actually evaluating a function. For example, let's say that we want to evaluate the function g at x is equal to 10. G of x is the function 2x plus 25. You plug in 10 for x, so now you're writing g of 10. So again, you can very clearly see I'm plugging in 10, that's an x value, and we're getting 45, right, when we do that. So 10, 45 is a point that's on the graph of g. You go over 10, up 45, there you go. That'd be a point on this specific line. Here's another one. Evaluate v of x when x is equal to a plus 1. So I'd replace x with a plus 1, and I would do this evaluation. Remember, a plus 1 squared is not a squared plus 1 squared. It's a plus 1 times a plus 1, which means you're going to have to do some box method or FOIL method, whatever it is that you prefer. But you're going to end up getting a squared plus 2a plus 1 minus 7, which will be a squared plus 2a minus 6. So our input is here. Our output is here. So here would be a theoretical point on the graph. We would just need to know what a is. The second useful purpose for function notation is that it gets rid of ambiguity between multiple functions. So for example, let's say we have this list of functions here, and I say, all right, evaluate the function at x is equal to 7. And you might say, well, which one am I evaluating? Right? And that's exactly my point. We don't know. I didn't specify which one you're supposed to be evaluating. But if we name them all, V, F, H, and G, and then I said, okay, now evaluate G at 7, well, then you can ignore all of these ones and just plug in 7 for this one. So being able to name the functions and refer to them by their name makes things a lot easier when you have a ton of functions and you want to focus just on one of them. Okay, so that's it. A little refresher course on what a function is, how you can tell if something's a function. And functions is basically what this pre-calculus class is about. Math 111Z is all about nonlinear functions, types of nonlinear functions. All right, so hopefully that was helpful. If you guys have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.